This is the CDFAM podcast with recordings from the CDFAM Computational Design Symposium held in Amsterdam in July 2025. The following presentation is by Momchil, Minkov and Qiqi, Wang of FlexCompute on real-time computer-aided optimization, how GPU native simulation changes the industry.
Hey, good morning, everybody. So I'm going to start our presentation by FlexCompute, titled Real-Time Computer-Aided Optimization and How GPU Native Simulation Changes the Industry. My name is Qiqi Wang. I'm a professor in aerospace engineering at Massachusetts Institute of Technology. And I co-founded FlexCompute a little bit more than 10 years ago. So today I'm going to present the vision of how FlexCompute aims to change how we innovate in hardware and through computer-aided optimization. And Momchil is going to give us specific examples in electromagnetics of how we are doing so right now. Why is hardware innovation slower than software? So when I was a kid, I have been reading various science fiction novels, and according to these novels, by today, 2025, all of us should be able to be taking vacations on the moon or Mars. And a lot of us should have flying cars to go around, not being stuck in traffic. Somehow this didn't happen, right? Instead, something else happened. What are these something else? I didn't have internet when I was young, now we do. We didn't have social media when I was young, now we do. And AI was not a thing when I was young, and now we have AI. So these are software-related innovations that are happening at a much faster rate than was envisioned when I was young. While hardware, aerospace particularly, and others like energy, transportation, it's much slower than what we have expected when I was young. I have been thinking why that has been the case. So I was in Stanford University for my PhD in aerospace engineering, and then I was in MIT for the last 16 years as a professor also in aerospace engineering. I have been observing like all the best students, PhD students in aerospace engineering, they did not stay in aerospace engineering when they graduate. They went to places like Google, Facebook, now OpenAI. And why is that the case? It's the case for a lot of reasons, but the fundamental reason is the following. So if they join OpenAI today, if they work very hard, have very good ideas, with a little bit of luck, their product, what they make, may be able to influence millions of people in a year or two. Okay? But if they go to aerospace engineering, at least 10 years ago, that was the case, you'd be very lucky if what you work on impacts a lot of people in like 10 years. So why is it the case? It's because working hardware is risky, right? A lot of people lost their lives testing very innovative ideas. It costs a lot of money, and it just takes a long time. So this is the fundamental reason why a lot of good people, they don't want to work on hardware, they want to work in software. And this is what we want to change as FlexCompute today. So the dream of why we founded FlexCompute was we want to make hardware innovation, innovating in like aerospace, to be as easy as innovating in software for the past few decades. We want to make it as easy in the next few decades. So I'm going to go really quickly through what we have already achieved because Momchil is going to give us more. Basically, we developed GPU solvers that accelerates simulation by a factor of 100. That was 10 years ago. Back then, nobody was doing GPU for simulations, and while at the same time reducing computational cost. And today, our two products, Flow360 and Tidy3D, are being used by a wide variety of industry partners doing very innovative stuff. If you look at the logos, they are probably the most innovative partners in the aerospace and electromagnetic industries. And something that we're specifically targeting for aerospace engineering is that the traditional way of designing aircraft and the spacecraft is really difficult as long as you move past the conceptual design phase. The disciplines have very big barriers. What we are trying to do is using what we call intelligent geometry to unify these disciplines, to break the barriers between disciplines and really enable innovation to happen in aerospace industry. And Momchil is going to give us a different example of enabling people to innovate in electromagnetics.
Thanks for the introduction, Qiqi. Yeah, so my name is Momchil. I'm leading the development of the tidy 3D solver at FlexCompute, which is, as Qiqi explained, focused on solving electromagnetic equations, as well as some other coupled multiphysics. And I realized that we've seen a lot of mechanical engineering, for example. We haven't seen any electrical engineering here, so I still hope that this will be useful for people in the broader ideas of what we're doing. But as a bit of a background, some of the markets, the main markets that we're targeting, or the main big market is photonic integrated circuits, and some specific applications include optical interconnects. This is probably the biggest chunk, which is becoming ever bigger actually because of the ever increasing needs of for data centers specifically. So AI is now in many cases bandwidth limited actually, and the optical interconnects are moving closer and closer to the electronic chips. There's a lot of innovation happening there, both from big companies and from startups that are by now already turning into big companies themselves. But other applications also include LiDAR, which is also obviously very hot right now for self-driving cars. And also quantum computing, we have some customers. A lot of basically doesn't matter what quantum technology exactly you're pursuing, you're always going to be using electromagnetic waves to either use as qubits or to access or connect your qubits. So in this photonic integrated circuit domain, there are design challenges on various different levels, as is true for every industry. In general, I've grouped them here into several different categories. Some are on the device level, where individual components need to be simulated, optimized, and also made in a way that is robust with respect to the foundry processes. So chips generally have very specific requirements, and every different foundry has different fabrication requirements that are very stringent, and making the designs that can meet those requirements while still being very optimal is actually very challenging. On the system level design, once you have the individual components, you're still not done, obviously. You have to be able to lay out giant circuits of millions of these components, make sure that everything works right, make sure, again, that it's also optimized. And also, there's a lot of communication here that needs to happen. Actually, that brings me more like to the workflow level. This whole process couples a lot of teams, or a lot of people within a team, a lot of teams within a company, and also there's a lot of communication that needs to happen between, let's say, the fabs and the designers in a given company. So there's challenges across the board. Yes, I'm going to focus on the first part here for the exact case study of what. So I wanted to hover my mouse, but I don't know if that's a good idea. Oh, there we go. Yeah, I'm going to focus on the first part, the device level simulation and optimization, as a case study of a recent innovation that we've introduced in this specific domain. And that's something we call inverse design for everyone. Now, I realize that in mechanical engineering, people are quite familiar with topology optimization and inverse design. The reason we call it for everyone is because in the photonics industry, actually, that was not the case. So topology optimization is not widely used. And part of the reason are those stringent requirements of the fabrication processes. So this whole device that I'm showing here is actually on the scale of a few microns. So that means that the features of the topology optimized structure are on the scale of tens or up to 100 of nanometers. So this is very, very hard to fabricate in a reproducible way over millions of devices. And because of that, inverse design topology optimization has generally, in photonics, been very interesting on the academic level for decades, but pretty much not used at all in industry. I guess for two reasons. One is ensuring this manufacturability and reproducibility. The other is also, it's been a bit intimidating for people. It kind of feels like, you know, if you did your PhD in that domain, you can do it, but otherwise there really aren't any tools that can do everything for you automatically if you're like a design engineer, but you don't have any specific skills related to inverse design. Yeah, so by inverse design generally we mean being able to search a relatively large parameter space, so a large number of parameters automatically, let the computer figure out what's best, but also it has to be constrained to the fabrication specifications. And typically, and also in what I'll be presenting right now, typically this would use some sort of gradient-based optimization, because if you have too many parameters, you need some way to navigate the parameter space. And specifically the adjoint variable method or automatic differentiation, or it's a related concept, I guess, is the way that this can be done efficiently, so gradients can be computed efficiently. Yeah, so in short, the legacy inverse design has been quite complicated to implement yourself, hard to control on what is going to be produced and whether it will fit the specifications, and slow using traditional computational methods. As Qiqi pointed out, we've definitely fixed the slow part of it because the initial offering of the company essentially, well, the initial fundamentals of the company were developing GPU native solvers. So compared to traditional tools, you know, you can get orders of magnitude speed up. And then we're also solving the other two problems of legacy inverse design. And that's why we call it inverse design for everyone. So I can skip over this and go over a specific example. So for one component, for example, that is very common in these types of devices is a grating coupler in which you have light coming from above and you want to couple it on chip. So this is basically crucial to couple in and out to optical fibers, let's say, to couple across chips, across racks, and so on. So if we can compute the gradient information, so this is actually a parameterized design, so that's even nicer. So here you're not doing topology optimization per se, in that your parameters are actually the primitives of just the spacings between the separate teeth of the device. But yeah, so if you compute gradients efficiently, that's great for two reasons. One is right away you get sensitivity analysis. You know how much let's say the width of each tooth affects your objective function or the coupling efficiency, and you know where to focus on. But then even better, you can actually plug this into a optimization routine, do some iterations, and get a much better design than your starting design. And then I think one of the innovations that I'm most excited about essentially is that we've made simulations largely differentiable, by which I mean that setting up a simulation is all you need to do to be able to also to compute gradients automatically. So this, I'm going to try to do this again with the mouse. Let's see what, okay. So in Python, for example, in our Python interface, what you need to do is define some functions that maybe create the teeth based on some primitive parameters like the widths and the gaps, creates the simulation in tidy 3D. Now all this is pseudocode, obviously, but the point is that this simulation creation, most of the simulation components are can be tracked in our automatic differentiator, such that the whole chain of parameterization, simulation, getting the results, which is actually typically done through a code to our web.run function. So this actually uploads the simulation to our cloud. The results get, it runs fast on our hardware. The results get downloaded. This is also part of the computational graph. And then finally, you can have as complicated as you want objective function figure of merit. You can even combine data across multiple simulations. Everything is going to be tracked. So you can do you can have a Monte Carlo run of multiple simulation as part of your whole objective function. You can then, as easily as calling this function to get the results, you can call a gradient function that will also get you the gradient of the figure of merit with respect to the input parameters. So that's why we also call it sometimes the PyTorch of photonics, because if you've ever done a machine learning model, probably you've used PyTorch, but even if you've not, what you do there is you define the model, you define the computational graph, and you don't have to worry about how to compute gradients. Basically, anything you define, you can call grad on, and you can get the gradient, and you can optimize it. And it's exactly how it works in iteratively, but with differentiable simulations. And in machine learning, essentially automatic differentiation is called backpropagation. It's the same thing. Reverse mode automatic differentiation specifically. It's the very efficient way to compute gradients. It's probably not an overstatement to say that backpropagation has enabled AI. And yeah, so we provide seamless interface as I said, in Python, it's basically equivalent to defining a simulation. You can then compute gradients. We also provide a GUI interface for that. And then importantly, we also provide essentially ready-made functionality that you can define fabrication constraints like minimum radius, minimum distance between features, and so on, that again, you just only define these primitive parameters and everything will be tracked and included in the optimization. And also we have several different algorithms, so topology optimization is certainly one thing you can do, but shape optimization, so for example, moving these feet around without really going freeform, can often produce much better designs in terms of fabricability and also level set optimization. And this is a quick example of how the teeth are moving around, and I'm going to skip to a topology optimization also example. Here again, so remember this is on the micron scale, but the objective is to optimize a meta service to focus the light injected from below to look like the FlexCompute logo, which is achieved here. And finally, we also have another tool that we call TidyFab, which can actually, and here we really work with the individual foundries to get statistics. This is usually proprietary information, but when we have collaborations with foundries, we can incorporate these statistics into our tools for specific fabrication process on various uncertainties that one might have in the fabrication process that can also be, again, incorporated in the simulation and in the optimization, such that maybe you won't get the most optimal design possible, but you will get something that when you fabricate, you know you will get very close to the target results, while if you don't include these things, it might look great in simulation, but then in practice it will not be very good. So going back to the challenges, yeah, I had to focus on the first part, the device level, but yeah, we have multiphysics, plus fast optimization of several different solvers that are GPU native, and then the automated optimization. On the system level design, we have a design and layout tool that actually wraps on top of all of that, and also facilitates the working with foundries. And finally, on the workflow management tool, we are also cloud native, and so we have a lot of the perks that come with that in terms of collaboration. And that's it. Thank you.
To learn more about the CDFAM Computational Design Symposium series, to see the archives of previous presentations, and to learn about future events, visit cdfam.com.